Swayam Prabha. Digital India. Educated India.
If you observe the program more carefully, what we want to know is, beyond this program point, which are the memory locations that are required by the program, and those are the memory locations that must be retained, everything else is garbage and it should be reclaimed, right. So, if we assume that this condition is false, for just to examine this case, let us look at this. If this condition is false, it means that x will continue to point to where w was, this assignment will not be executed, and we are going to access y, we are going to access y dot lptr. So, we are going to access this m, and then we are going to access x and y. So, blue nodes are the nodes that are used by the program, rest of the nodes are not used by the program. Of course, it is under the assumption that this condition is false. It is possible that the condition is true, right. So, let us see what happens when the condition is true. If the condition is true, x moves rightwards, this entire wave of usage move rightwards, and then we find that these blue nodes are the ones that are used, white nodes are the ones that are not used. Now, in order to over approximate at compile time, we could say I do not know whether it will execute or not, but let me consider both the situations. Let me take a union of both the possibilities, in which case blue nodes are the only nodes that are not garbage, every white node is a garbage, but no textbook will define it as a garbage. Can we do something about it? Can we devise a program analysis that says that white nodes are not required, I need only blue nodes, and if I can figure out I need only how to identify only blue nodes, then I can get rid of a large chunk of memory, I can bring down the footprint of memory footprint of my program, I can make the program run faster because I might need fewer garbage collection cycles, right. So, this is the memory optimization that we are talking about. Let me skip some of these slides. So, the whole idea is, so what is the difference between these white nodes and blue nodes? The essential difference in these nodes is that these blue nodes depend on the usage in the program beyond that program point, and white nodes are the nodes that depend on the connections that have been made in the past. So, when this problem was first posed to me, someone said that we look at the connections made in the past, and depending on the connections we say, okay, this is not required and let us get rid of it. I found it a little bit odd. Why is it odd? Because past behavior of the program was being used to predict the future behavior of the program. Okay? Future was being approximated by the past. We do it all the time. See, in the midsem exam, you got 70 marks. So, in the endsem exam, how do you expect to get 95 marks? You do it all the time, right? But the question is, can we do something better in program analysis? So, we have to be able to make this distinction between the memory that has been created and the memory that is being used. So, we call them as reachable versus live, and if you look at the standard glossary of terms, etc., they say live or memory or an object is live if the program will read from it in future. The term is often used more broadly to mean reachable, and it is not possible in general for garbage collectors to determine exactly which objects are still live. Instead, they use some approximation to detect objects that are provably dead, such as those that are not reachable, and this is something that I do not agree with. This is something that, because people did not know how to do it, does not mean that it cannot be done. So, we want to look at how we can do this. I do not think I would have time to go into all the details of how we achieve it, but I will try to fit in whatever we can. So let me skip. So there have been lots of studies which say that this is an important problem. Let me skip all of it. So before we talk about the liveness of heap data, let us simplify the problem. Let us first talk about the liveness of stacked data. Okay, we will worry about the heap later. Okay. What do we mean by liveness of stacked data? We are trying to ask a question: is the value inside a variable, value in a stack location, is the value of a variable used in the program beyond a given program point. So in order to make the problem more interesting, we have changed that if to while, and we are showing this stack this way. So what is the meaning of the use of data? We are essentially saying, are we reading the contents of a location? That is the meaning of accessing the location and reading its contents. If we access the location and read its content, we might access a location to know its address. That does not make the location live. It is only when we dereference that address and read the contents that makes the location live. Okay, so let me skip the details. So let's look at this intuitively. So here, so I have now created a control flow graph of the program, and for simplicity I have taken a basic block as a single statement. I could have combined things, but explanation becomes easier if we take a single statement as a basic block. At the end of the program, no variable is live, no variable is used beyond this program point, right. So the way liveness analysis works is, we know that at the end of the program nothing is required, and then we step our way backwards in the program by saying nothing is required after the last statement. Let us find out from that nothing what is required for the execution of the last statement. So effectively what we are doing is, we are picking up a statement, we are saying we know what is live after the statement, and from that we compute what is live before the statement by incorporating the effect of the statement on what is live after the statement. Right? That is the general principle that we use. So let us run through this program. Now if nothing is live here, what do you think should be marked as live here? Which variables should be marked as live? X, Y and Z. Are you sure Z is live? Z appears on the left hand side, by the way. We need the location. Okay, what you are saying something? Y, yes, Y is live. Is X live? X is not live. Okay. Z, is it live? What does liveness mean? Here is a litmus test of liveness. If you put a garbage value in some location and the program happens to read it, then the variable is live. If you put a garbage value in a variable and the program does not happen to read it, then it is not live. Now with this definition, will you say X is live? Yes. Will you say Y is live? Yes. Will you say Z is live? Unanimous no. Anyone wants to rethink about it? If I put a garbage value in Z before this statement, will I have the right behavior of the program? Why yes? I will end up putting the value, the result somewhere else. Z is being read. Although Z appears on the left hand side, the value of Z is being read and the offset of sum is added to it in the structure, and that is where the write is happening. Z is not being written into, so Z has to be live. Yeah, you don't seem to agree with it. Okay, so we will mark X, Y, Z as live. We show live nodes as blue nodes. Now tell me what all will we mark live here? before this statement y is equal to y dot LPTR? Yeah. Could I repeat that z? Yes. Okay. So, let me use a, do I have a pen? I can use the board. Yes. Okay. So, what makes a location live is that if we have some content in the location and that content is required by some other statement below it. Okay. So, for example, if we have let us say this is A, okay, and if we have the statement A is equal to 10, okay. This is the location. So, we have A is equal to 200. I am simplifying the matter. Now, I am putting this value 200 in A. In this region, do I need the value of A? Assuming that there is no other statement that reads the value of A, I do not need the value of A, right. This is overwriting the value of A. So, whenever a value in a location is overwritten, in liveness analysis we say the liveness is killed, right. So, a location is not live because of one of the two reasons, either right from the end there is no use of it, or there is use of it, but the value has been overwritten. So, if I am saying print A here, I am going to print the value 10 and not 200, right. So, here x is not live, here A is live, right. So, either there is no use or the value is overwritten, right. Now, let us come to, so this was a scalar variable, let us come to structure variable. So, we have Z points to some location whose field sum, the result of the addition is being stored here. This is the destination. This is the location that is being overwritten. Z is not being overwritten. If we put a garbage value in Z, what will happen is this connection will be severed and instead it will start pointing to some other location and we will end up putting the result here instead of here, right. So, when a variable appears on the left hand side, you all know what is R value and L value, right. It is a tricky definition. It is a tricky definition because everything that appears on the left is not an L value. In particular, in this case, Z dot sum is not an L value, or rather Z is not an L value, Z dot sum is an L value. Z is still an R value because this, until you read this, how are you going to reach this location? So, Z is being read, Z is not being written into by this assignment statement and therefore, Z is live, Z is made live by this particular statement. Does that answer your question? Okay. So, now going forward, how do we, what do we say about liveness here? I just now said if a variable is being overwritten, its value is not required. So, what would you say about liveness here? What is live? Let me ask a simple question. Is Z live here? Yes or no? Yes, because from this point onwards until here we need the value of Z. Is X live here? Yes. Is Y live here? No? Wonderful. I managed to divide the class again. Live, yes or no? Yes. Anyone who wants to say no? Why live? Let me hear from the yes camp. Yes. So, although the value of y is being overwritten, we have to keep in mind the semantics of the assignment. The right hand side is evaluated before left hand side is written into, and in order to evaluate the right hand side, we actually are reading the value of y. So, when we have the same variable appearing on both left and right hand side, it is clear that the variable continues to be live. The value of y has changed here, right. The value of y has changed here, but we are not asking a question, has the value of y changed? We are only asking a question, is the current value of y required? So, y may be live here, y may be live here, and the values in y may well be different. We are not talking about the values in y, we are talking about only about the use of values in y, right. So, y is live here. Now, what will be live here and what will be dead? Tell me before this assignment statement. Z will be dead. Now, everyone is an expert on liveness analysis, wonderful. Z will be dead, X and Y would be live. What will happen here? X will be dead? No, very good, resounding no. Y will be dead? Yes, very good, resounding yes. So, we will have only X as live, okay. And now, here is a tricky situation. Liveness depends on the statements executed after it, and we have not really looked at this statement, and this statement is going to be executed after it. For simplicity, let us assume that nothing is live here, okay, and we will justify that later. So, then we will have X as live here, and now here we will say if the program executes along this path, X is live. If the program executes along this path, X is live. So, we combine the two and we say X is live here. This does not overwrite anything, so liveness does not change. So, we have X is live here and we have X is live here, right. So, that is one traversal over the program in a backward direction against the control flow. Why against the control flow? Because we are predicting the future. We are not recording the past behavior of the program. We are trying to predict the behavior of a program beyond a given program point, and therefore, we are traversing the program in a backward direction. So, this is the result of one traversal over the program. So, we marked what is live here and what is not live here. This is end of iteration 1, but note that here we said X is not live, whereas actually if because X is live here, X should be marked as live. So, we reiterate over the program, we compute the values again, and the only change that happens is this, and we get this liveness, and this analysis concludes, right. And we are going to do more of it, we are going to look at it, going to define it more formally later, but this was just to introduce the notion of what is liveness and how do we do liveness analysis of stack variables. Let us get back to heap data. Okay. Any questions about this? Just make sure that we are on the same page. I do not want anyone to be left behind. We are all okay on this? Very good. So, now let us talk about heap data. So, we had blanked out the heap and we are talking about the stack. Let us see if we can repeat the same thing for heap data. So, we had seen that if the while loop is not executed even once, these are the locations that are being used by the program. We had seen it before. What would happen if the while loop is executed once? We will have this entire wave will move rightwards by one location, right. But at compile time, we cannot assume that while loop is not executed even once. It is a compile time analysis, we cannot make assumption about runtime behavior, you cannot constrain runtime, right. So, if the while loop is executed twice, we will end up. How do we do liveness analysis for this? In the case of stack, it was all nice, you knew X, X is red, yes, X is red, but now here the locations that are read keep changing with iteration of the loop, and that is a problem. The trouble is that in case of heap data, an L value and its address, or rather address expressions and the value that they hold, the mapping keeps changing. So, here x points to A in this case. So, x holds the value of A, perhaps x would hold the value of B, perhaps it would hold the value of C. So, x is an address expression. Similarly, x dot rptr is an address expression, and these address expressions evaluate two values. So, if we talk about what value is being used by finding out going through the address expressions, we get into trouble. We get into trouble because x at one point of time holds this value, x at some other point of time holds that value, right, and we cannot perform static analysis. That is the trouble. With the stack there was no problem because the address of x is fixed, its value might keep changing, the address of x is fixed. It will always be at an offset of 14 from the stack pointer in every invocation of the in every invocation of the function, that is clear. In case of heap, now we have a trouble. In order to perform static analysis, we have to name the locations. So, because for stack variable the offset is fixed, we can name those locations by the variable names. Now, these are unnamed locations. I have given them names A, B, C, not because they are program names, but for convenience. They are all unnamed locations. And when we have unnamed locations, how do we name it? So, we say, okay, this is a pointee of x, right, but the pointee of x is actually B sometime, the pointee of x is something else. So, the names, the location, heap locations cannot be named, and therefore, we cannot perform static analysis so easily, right. So, let us look at what our solution is. So, this is what I was saying. So, we update the program, we instrument the program and insert these assignment statements. To make it more concrete, I have put this return z dot sum, so that one should not say that this assignment is redundant. So, these are all the assignment statements inserted by the program, by our analysis. Okay. Now, I have to convince you that this transform program is indeed a valid program, or you have to convince me that it is not a valid program. So, let us examine some interesting assignments. So, we are talking about if the while loop is not executed even once, this part will not be executed, and we are looking at memory just before statement 5 as it would exist, but let us execute this program. Assume a situation, assume a program run where the while loop is not executed even once. So, this w equal to null is going to cut away this link, right, easy to see. Then this while loop is not going to execute, so nothing will happen here, but we will have x dot rptr, that link will be cut, and then x dot lptr dot rptr, this link will be cut, right, and then we will have this link x dot lptr dot lptr dot lptr will be nullified, and then x dot lptr dot lptr dot rptr will be nullified, right, and then y will start pointing to it, and this x dot lptr will nullify this, y dot rptr will nullify this. By the time we reach statement number 5, this is how the memory looks. Right? Everything that is unused has been made unreachable, and therefore, any garbage collector can collect it. All we are trying to say is, if a memory location is being used, we need to retain its connection. If a memory location is not being used, let us remove its connection. This is what it does, right. Any questions? Well, if you do not have a question, then I have a question. This is under the assumption that while loop is not executed even once. What happens if the while loop is executed once? This program has not been generated with that assumption in mind. Will this program still work if the while loop were to execute once, or will it create trouble, will it bomb? What is your guess? Will it raise an exception, or will it work? It will work? Do not say just because I have shown it, so it will work. You have to give me a reason why it will work, or you have to give me a reason why there will be a problem. Will it work or will it create a problem? It will work. Why? Yes, because this wave will shift rightwards. Some other locations, some other connections will be severed, some other links will be nullified. Remember, we are nullifying x dot rptr. We are not asking a question, where is x pointing to? What is the value of x? It took us 1.5 years and one M.Tech project to realize that the question that we should be asking is not what is the value of x. The rest of the world could not get this because they kept on asking this question, what is the value of x? But the trouble is, the value of x is not an invariant of the program. Value of x keeps changing. At the same program point in different runs of the program, value of x keeps changing, and if it is not an invariant, you can't do static analysis. A static analysis can only find invariants in a program. If there is a property that holds across all program runs, then you can find it. If there is a property that does not hold along across all program runs, then you cannot find it. You have to over approximate it. Simple principle of static analysis, right. So, it took us 1.5 years to realize that instead of asking what is the value of x, we should be asking, am I dereferencing rptr out of x or lptr out of x in the program? That is an invariant because the programmer has written it in the program. The programmer said here, no matter what the value of x is, I want to read rptr. That is an invariant. The value in x is not an invariant, but whether we are reading rptr out of x or lptr out of x, that is an invariant, and that is our only hope. So, our analysis essentially tried to find these invariants, and therefore, was able to manufacture this nullification statement. So, this will work, it does not. In fact, this nullification writes the program execution. If x points here, fine, rptr will be nullified. If x points here, does not matter, rptr will still be nullified, because I know that that is not being used, it is the lptr link that is being used, right. So, this is an example of a modern analysis that goes far beyond liveness and available expressions analysis, etc., that we are going to see, right. So, the memory address that x holds when the execution reaches a given program point is not an invariant of program execution. Whether we dereference lptr out of x or rptr out of x at a given program point is an invariant of program execution. A static analysis can only discover invariance. More importantly, a static analysis can only discover some invariance. You have to weaken the conditions in order for a static analysis to discover it. Okay. So, what is static analysis of heap? Let us look at the two worlds, there is a static world and there is a dynamic world. Okay. In the static world, we have a program code. In the dynamic world, we have process. We have programs in execution, right. In the static world, the program is characterized by being abstract, because I do not know what the value of x is. It is bounded because every program is finite, program text is finite, there is a single instance of the program. Correspondingly, in the dynamic world, process is concrete because I know the x, the value of x is 5 here, right. It is unbounded because I do not know whether the program will ever terminate, whether the process will ever terminate. Okay. And there are infinitely many execution instances that are possible for this program. Now, each of these processes would create heap memory of a similar nature, memory that is concrete, unbounded and infinitely many. And we want to summarize this in the static world. What the rest of the people were doing were, they were trying to do profiling and do this. Instead, we decided to stay in this world and we said, let us look at the program and let us try to get the summary data out of the program. That is program analysis and that is heap data analysis for us. If possible, I will try to go to the details of how we have arrived at these nullification statements, but I am not very optimistic about it. We have too many things to cover and we have limited time. What we are going to do in the next this thing is, we are going to talk about this soundness and precision, and now I am going to go into more abstract things. I will try to bring out concrete examples, but it is going to be a deeper discussion than what we have done now. So, any questions on what we have seen so far? Okay, so let us break for tea.